Good morning, everyone. I am Prasanna Kumar from the Department of CSM Section C. Today, I'll be presenting on the topic Faster Algorithms for Eulerian Circuit Detection in Dense Graphs under the course of Essentials of Problem Solving. This presentation focuses on improving computational methods used to detect Eulerian circuits efficiently in dense graphs. Let's begin by understanding what an Eulerian circuit is and why detecting it efficiently is such a challenge, especially in dense graphs. Introduction to Eulerian circuits. An Eulerian circuit is a closed path in a graph that visits every edge exactly once. This concept introduced by Leonhard Euler in the 18th century. This forms a foundation of graph theory. Eulerian circuits have several real-world applications such as network routing, DNA sequencing, and circuit design. Our goal is in this presentation is to explore how we can make the detection of these circuits faster in dense graphs where traditional algorithms become slow and inefficient. Basic definitions and properties. A graph To recall, a graph has an Eulerian circuit if and only if the graph is connected and every vertex has an even degree. In dense graphs, the number of edges is very close to the maximum possible, meaning the graph is nearly complete. This density creates challenges because the algorithm must be a process of large number of edges, often proportional to traditional algorithms that work well for sparse graphs tend to perform poorly here. Challenges in dense graphs. In dense graphs, we typically deal with millions of edges in large systems such as social networks or bioinformatic datasets. Checking all edges and vertices becomes computationally expensive. Naive methods have quadratic or even cubic time complexities. Hence, our main challenge is can we detect Eulerian circuits faster while maintaining accuracy? Existing algorithms overview. One of the most well-known algorithms for finding Eulerian circuits is Hierholzer's algorithm, which runs in time, where where is the number of edges. However, in dense graphs approaches, making it computationally heavy for large inputs. There are heuristic and approximation algorithms, but they make sacrifice precision for speed. Thus, the search continues for algorithms that are both accurate and faster. Motivation for faster algorithms. The motivation is clear. Speed and scalability. Faster algorithms can handle real-time applications like dynamic network updates, manage large datasets efficiently, reduce processing costs in practical systems. The aim is to exploit unique properties of dense graphs to outperform traditional approaches. Key insights and theoretical foundations. Dense graphs exhibit high connectivity, meaning almost every vertex is connected to most others. This property can be exploited in algorithm design. Moreover, spectral graph theory, which studies the eigenvalues and eigenvectors of graph matrices, offers powerful analytical tools. Additionally, randomized and algebraic techniques open doors to new and faster solutions. Algebraic approaches. Using adjacency matrix algebraic methods can detect Eulerian properties through matrix operations. Techniques like matrix purging and eigenvalue analysis reduce the problem to linear algebra computations. These methods can sometimes detect Eulerian circuits faster than traditional traversal algorithms in dense graphs. In algebraic matrix methods, we represent a graph using an adjacency matrix and use matrix operation to analyze it. For example, Matrix powering helps identify connected paths. Eigenvalue analysis can reveal symmetry and structure. By transforming the problem into linear algebra computations, we often achieve faster detection, especially with optimized matrix libraries. Spectral algorithms. Spectral algorithms analyze the eigenvalues and eigenvectors of the graph, Laplacian or adjacency matrix. Such algorithms can quickly identify structural properties relevant to Eulerian circuits. Spectral algorithms are based on analyzing the graph Laplacian or adjacency matrix. The eigenvalues of these matrices reveal important properties such as connectivity and degree distribution. These methods typically run in time, but using advanced matrix multiplication or approximation techniques, the runtime can be improved. Spectral methods are particularly effective in identifying structural features that indicate Eulerian properties. Randomized algorithms and sampling. Randomized algorithms sample parts of the graph to infer Eulerian properties with high probability. These algorithms can often achieve subquadratic running times in dense graphs. Probabilistic methods provide a trade-off between accuracy and speed suitable for large graphs. Another emerging approach involves randomized algorithms. Instead of processing every edge. We randomly sample parts of the graph to estimate Eulerian properties with high probability. These methods often achieve subquadratic runtime such as while maintaining reasonable accuracy. This trade-off makes them attractive for extremely large dense graphs. Algorithmic frameworks for dense graphs. Combining multiple techniques leads to powerful frameworks. For instance, algebraic pre-processing can simplify the graph structure. Spectral methods can then quickly check connectivity and parity. Parallel computing or GPU-based computation can further speed up results. These frameworks represent the hybrid future for Eulerian circuit detection. Recent advances and results. Recent algorithms have achieved subquadratic runtimes for Eulerian circuit detection in dense graphs. These methods leverage structural properties of dense graphs such as high connectivity and symmetry. Theoretical bounds indicate potential for near linear time algorithms under certain conditions. Recent research has shown promising results. Some algorithms now achieve subquadratic time complexity for dense graphs. These advances rely on leveraging the high connectivity and symmetry within dense structures. Under certain theoretical conditions, researchers believe we could achieve near linear time detection in the future. Practical implications. Faster algorithms enable real-time analysis of large dense networks like social or biological networks. They reduce computational costs for applications in logistics, circuit design, and data analysis. Implementation considerations include optimizing matrix operations and leveraging hardware acceleration. The real world implications are vast. In social networks, we can model and analyze connections efficiently. In bioinformatics, faster algorithms can help in genomic sequencing. In logistics and circuit design, quick detection ensures optimized routing. However, these gains require hardware optimization and careful matrix computation techniques. Open challenges and future directions. Despite extending these algorithms to weighted or directed dense graphs remains an open problem. Improving probabilistic bounds for randomized methods can enhance reliability. Integrating these algorithms into practical software tools requires further research and development. Despite major progress, challenges remain. Extending methods to weighted or directed dense graph, improving accuracy of randomized methods, creating practical scalable software implementations. Ongoing researchers focuses on these aspects to bridge the gap between theory and real world use. Summary and conclusion. To summarize, detecting Eulerian circuits efficiently in dense graphs is a key challenge in modern graph theory. Algebraic, spectral, and randomized methods have shown significant improvements. Recent advances push us closer to subquadratic or near linear algorithms. With continuous research, we can expect broader applications and faster computation in real world systems. Thank you all for listening. I hope this presentation provided valuable insights into the advancements in Eulerian circuit detection. Thank you.